Hello everyone, we are True North Environmental. My group consists of Aisha, Greg, Cameron, Colemax, and me, Robbie. Right now we're in an overview design map of our project, which will serve as a virtual guide throughout the presentation as we take you along to show you our design, the gold mine tailings disposal and reclamation facility. For our group's Capstone design project,
it was assumed that a gold mine located in the Kenora region of Ontario
was operating at a capacity of 10 times its current rate, effectively producing 40,000 tons of tailings per day. The goal is to design and develop a tailings management process for the mine's entire design life of 31 years, and then create a closure plan to reclaim the land and its natural vegetation. The design is to be created to be both feasible and safe for the surrounding environment and Indigenous communities. So what are tailings? Tailings are the mine waste left after the desired material is extracted from ore. And since this is a gold mine, there would typically be high levels of cyanide. A large amount of water is also used in the extraction at the mill, so the output tailings are then in the form of a slurry. Environmentally, there are a lot of important things that must be evaluated for the design, such as the stability of the tailings in the storage embankment and the leachate that could seep into the groundwater. If the tailings go untreated, the slurry's high water content is prone to liquefaction, which can cause dam breaches and be very harmful to its surrounding areas. The dam will also require constant monitoring for the foreseeable future. For this reason, the design that was chosen for processing the tailings was to develop a dry stacking facility, which effectively dewaters the tailings to eliminate the risk of liquefaction. Now we're going to get into the technical part of our design, which will start off by Greg talking about the slurry pipeline.
You can now see the two pipelines that will be transporting the tailings slurry to the tailings treatment facility. When choosing the design for the pipeline, the following criteria was taken into account. The materials of the pipeline must have adequate strength and resistance to abrasion and corrosion. The tailings slurry must travel above a certain velocity for the tailings to stay suspended and not settle, which would result in clogging. Heavy-duty slurry pumps are required since they are designed to deal with fluids with high solids content. The net positive suction head must also be above the value indicated by the pump manufacturer, also known as the NPSH required or NPSHR, to prevent cavitation, which results in rapid wear of pump parts. Other factors were selecting an economic design, choosing realistic pipe diameters and pump discharge diameter, and accounting for head loss along the pipe. With this in mind, two 550mm HDPE lined steel pipelines were chosen to pump the slurry over a hill. The pipeline is above ground with a slurry velocity of 1.67 meters per second. Two slurry pumps will be on each pipeline 100 meters apart with backup pumps for each pump in parallel for maintenance and emergencies. The pumps will be located inside pumping houses.
As Greg mentioned, the pipeline feeds into the filtration facility for dewatering, which Cameron will now talk about.
Here at the tailings filtering facility, there are 19 screw press filters operating at 90 tons of tailings per hour to dewater the tailings. The slurry comes into the screw press filter and is augered to the other side, squeezing the water out of it, depositing a dry cake. The water that is removed from the tailings will be transported back to the mill with the smaller of these three pipes and be reused in this extraction process. The dry cake will be conveyed out and deposited, which Greg will talk about now.
Here you can see the conveyor system that conveys the dewatered tailings to the deposition stack, which consists of a mobile conveyor bridge and a spreader. The speed of the conveyor belt was calculated to be 1.03 meters per second to remain on schedule. The tailings would follow a deposition plan like the plan shown in the top right, where the spreader travels along the conveyor bridge to form stacks as seen in the bottom right image. And now I'll pass it back to Cameron, who will talk about the tailings deposition more.
Here the dry cake will be deposited at an initial height of 3 meters every year. Due to compression over the 31-year lifetime of the mine, the final height of the stack will come out to be just over 33 meters. An embankment will be created to support the tailings, and the deposition will be done in a Frustrem pyramid. This is to ensure there is a proper slope for the closure that Colemax will talk about later. On either side of the impoundment, there are ponds that will collect the runoff that comes off the impoundment. To ensure the runoff is directed to the Ponds, drains, and ditches are used to direct the water.
In case the dry stacking facility processes are experiencing any sort of failure, Aisha designed a method of accommodating for this, which she will now discuss.
An emergency tailings disposal pond was designed next to the dry stack facility to accommodate 5% of the total tailings produced over the lifespan of the mine. More specifically, the pond was designed as a backup disposal site for when any failure in the tailings treatment facility or transportation occurs. The pond is 1.5 kilometers wide and 2 kilometers long with a total depth of 6 meters. The main environmental risks associated with this pond are the resuspension of the tailings to the surface, where they can get oxidized and generate acid, directly posing a threat to wildlife. The seepage of the leachate to underground water, where it can contaminate the water supply and harm vegetation, is another concern. To mitigate these risks, a minimum 1 meter water cover is to be maintained at all times to prevent potential resuspension. This was calculated based on critical shear stress, which was determined using wind wave equations. Under the water is a 5.7 meter tailings layer, which was followed by a 0.3 meter sand liner. The last layer is a 2 millimeter thick high-density polyethylene geomembrane, which is represented by the red line in the schematic here. This geomembrane liner was selected as it combines strength and oxidative resistance and is not as ductile as other geoliners. Finally, monitoring wells will be installed around the pond to monitor the leachate concentration and ensure it is at the acceptable levels at all times.
From here, we'll move along to Colemax, who will talk about the closure of the dewatered tailings storage embankment.
Hi everyone, I'm Colemax and I'm talking about the slope stability and the land cover use. For slope stability, the main purpose is measurement the maximum stress before dam failure. Our design degree of the dam is 8 degrees. The height of the dam, the height of the tailing is 33.48 meters. So the basement of the dam should be 238.22 meters. The different color in the graph shows different materials. The left side is the tailings with different year, and the right side is the embankment. There are two different conditions using the slope stability test, which are drained and undrained. The differences is water, which is the wall ratio. For drain test, the water is fully drained out, so we need to add pHI and cohesion values. The minimum results of our testing is 4.8, which means the structure is very safe. For the undrained test, the water still influence on the structure. The minimum factor of safety is 1.27. It's still good because it's larger than 1. Lastly, I will talk about the topsoil molding and baseline conditions. There are two reasons. The first one is to make sure there have enough water in the dry season for revegetation, and the other reason is make sure the topsoil is unsaturated in the rainy season to avoid the water and the air connect with the tailings. Also, it can avoid runoff in the rainy stations. As you see, our topsoil is totally 1.4 meters, which includes 0.3 meters soil layer and 0.4 meters slate layer and 0.7 meters clay layers. Both slate and clay layers are good materials to contain water. Now I will back it to Robbie to do the conclusion.
So that concludes going through the technical parts of our project. In the end, the design is predicted to cost $2.74 billion when combining both capital costs and yearly operational costs over the life of the mine. However, since we're dealing with 10 times the actual amount of tailings that the mine produced, if it also collected 10 times the amount of gold as a mine has per year, it would make approximately $93 billion over its lifetime, when taking into account the average price of gold over the last 10 years. With the operational expenses amortized over the life of the mine, the management of tailings only costed 3% of the total revenue, which is considerably less than the industry average of 10%. So in the end, the design was successful and was proven to be quite feasible. On behalf of True North Environmental, we would like to thank you for listening, and we'd be happy to take any questions at this time.